Go ahead and do an example problem. This example problem reads, argon gas enters an adiabatic turbine at 800 C and 1.5 megapascals at a rate of 80 kilograms per second and exits at 200 kilopascals. If the power input to the turbine is 370 kilowatts, determine the isentropic efficiency. So let's go ahead and start with a schematic. If I draw a schematic of this turbine is producing an actual power output of 370 kilowatts with a pressure input of 1.5 megapascals and a temperature input of 800 degrees Celsius. And it has an exit temperature pressure of 200 kilopascals with a mass flow rate of 80 kilograms per minute. Now, with this turbine, we can draw several assumptions. One, I would assume that this turbine is operating at a steady flow. Number two, I would assume that the kinetic and potential energy change of the gas entering and leaving is zero. Number three, the problem statement tells us that this turbine is adiabatic, so there's no heat transfer. Number four, I would assume the argon gas to be an ideal gas. I'm going to go ahead and assume that that ideal gas has constant specific heats. Okay, so now the problem statement is asking us to find the efficiency of the turbine. If you remember back earlier, the efficiency of a turbine is quantified as the actual work over the isentropic work. Now, the problem statement gives us that the actual work is 370 kilowatts, but we don't know what the isentropic work is, right? So the isentropic work, again, according to first law analysis on an adiabatic turbine, would be the mass flow rate times the enthalpy going in minus the enthalpy going out, and that enthalpy going out would have to be for the isentropic process since we're trying to find the isentropic work. Now, with that constant specific heat assumption, we can go ahead and assume delta H to be Cp delta T. So what's left now is to find out what the temperature coming out of the turbine would be if the process were isentropic. Now, recalling back earlier, we went ahead and we quantified that there are three equations, and what I'm going to do is just scroll back to those equations. These equations here on this slide represent the change in temperature, right? How the temperature would be coming, the temperature at the end of a process, assuming an ideal gas, with constant specific heats, undergoing an isentropic process. Now, in this problem that we're doing right now, bear with me as I scroll back to the problem statement, we have here an ideal gas with constant specific heats, and we're trying to find the isentropic work, right? So if I'm trying to find an isentropic process with an ideal gas with constant specific heats, those assumptions are all valid here in order to find the temperature coming at the end of this expansion process in this turbine for an isentropic ideal gas, isentropic process for an ideal gas with constant specific heats, because I'm trying to find the isentropic work. So here I would have T2 over T1, again, this is for the isentropic process, equals P2 over P1 to the K minus 1 over K. So the only thing to do is to look up the K value in the ideal gas tables. I have P2, which is 1.5 megapascals or 1400 kilopascals. I have P1, which is 200 kilopascals. I can go ahead and directly solve for the temperature coming out of the turbine if the process were isentropic. So from there, I can go ahead and calculate, based on the givens in the problem, the isentropic work, assuming constant specific heats. If I were to do that and plug in my knowns, I'm not going to go through every step in the math, but if I do that and I find my unknowns, I find that if the process of this turbine were isentropic, it would put out a maximum possible 412 kilowatts. I would take that number, bring it back up, put it into this equation, right? So I get 412 kilowatts is the isentropic work, or the maximum work this turbine could put out. It's actually putting out 370 kilowatts. And so this turbine is operating at an efficiency of 90%.